Hello, everyone. Welcome back to this is now a Q&A session after Kaelyn's lecture. I'm Fabio Scafirimuto. In IBM Quantum, I lead a team that focus on education, outreach, workforce, and advocacy activities in EMEA. I work with many people, including also Kaelyn, that is now again on stage after the lecture. Maybe Kaelyn, you can say a few words also on yourself and what's your role.
Yeah, sure. So like I mentioned at the beginning of my lecture, I'm a sort of research software engineer. The team I work on is mostly focused on writing out all of the software documentation for all of our different products. And so I help maintain the website infrastructure to a degree, but mostly write content for it. And then kind of do a variety of little sort of like software engineering kind of projects on the side.
Oh, perfect. I think this would be already inspiring many questions from the audience. But I see that
Excellent.
we have already so many, so I'm not sure if we
A
will be able to
lot. Yeah.
cover them all. I see several questions coming up, so I guess we'll just start. And then if there is some time at the end, maybe we can also ask some career question, maybe based on your experience, some advices for the audience.
Yeah.
But let me start from, okay, there is an order based on how many clicks we got. So question number one is, what are some real life problems quantum computers have solved till now?
That's a good question. So I think it sort of depends on what you mean by solve technically, because the types of problems that we can tackle with quantum computers right now can be approached using classical approaches, usually clever ones. We're like you've maybe seen a lot of this sort of like messaging about like utility scale quantum computing, which is the point at which the work that quantum computers can do is either meets or exceeds the sort of like brute force kind of like approach that you would typically do with numerical techniques. But we're still, once we get to that point where quantum computers have a problem that can be solved without without a classical approach or without an equivalent one, that's the sort of arena of quantum advantage, which is what we're working for. And hopefully, we've announced, I think, that we'll get to it sometime in 2026, perhaps.
Really exciting, huh?
Yeah.
Perfect. We got so many. I doubt we will manage to go
Oh,
through
yes.
through them
Yeah.
all.
Oh, certainly not. Yeah. Let's go for
So
the
let's go to the
highest
next.
voted ones, I think.
Yeah. So the next one is, what's the best approach to understand quantum simulations for a complete beginners, especially to understand the lecture material covered today?
Yeah. So I think I would say, especially if you're a complete beginner, I would go with looking up sort of like undergraduate textbooks. Griffiths is sort of like the canonical one that like every undergraduate uses to learn quantum mechanics. We also have our learning materials as well on the IBM Quantum platform. John Montrose does an excellent job of doing a lot of sort of building the foundations of like how quantum mechanics works and how to use it. And then I think to dive into quantum simulation, the thing that I would specifically look towards is thinking about what types of systems that you want to simulate, or maybe what approach you want to try to learn how to use to simulate quantum systems. Because I think in my lecture, I kind of created this kind of general framework for how quantum simulation works, but I haven't seen a lot of textbooks that are structured in that way and that are very general. And they're usually like quite specific. So you may want to find a book on condensed matter physics if you want to try to dive into density functional theory, or there's a number of texts on second quantization, I think would be another sort of arena to look into. Um, and once you get into that area, that's the point where like you'll find probably less like video content or video lecture material, and then you'll kind of have to like dive into like textbooks or other like written works, I think.
Yeah. I fully agree. I think a combination of textbook and the courses, for example, the available material we have online. And
Yeah.
actually, I want to add maybe two that came to my mind. We have two courses, one on VQE and another one on SQD, or actually diagonalization algorithm, that I think
Mm-hmm.
really would be very nice complement to what you basically have introduced to today.
Yeah, that's true.
So
Oh,
maybe
there's
yeah,
one more
you check
actually
it
too
out.
that I can think about. So Olivia Lanes has a course on, I think, practical quantum computing,
Yeah.
or quantum computing in practice. And I know at least one of her lectures focuses on quantum simulations sort of as a topic, which I think could be good too.
Mm, mm. Yeah, that's another good tip. All right, let's move on. Actually, that's also a good suggestion because I've seen before that many people ask about resources, and I think
Mm,
we've covered that part. So let me pick another question. Um, if I want to treat into if I want to tread into quantum dynamics, what resources would you recommend? So more specifically about dynamics now. I'd love to
okay.
understand today's lecture in full depth.
Yeah. That's also a good question. I think I would say similarly get like a sort of like a foothold on quantum simulation generally. And the thing that you'll have to kind of like look into a little bit more with like thinking about quantum dynamics is sort of what are the application areas for quantum dynamics? Like, what are you trying to characterize when you're trying to do some kind of like dynamics experiment in some way? And for those, I think you could look into. There's a number of topics within condensed matter where dynamics can be helpful, and like this thing called response functions, as well as spin systems are another one that are sort of like another topic that like quantum dynamics is used for. I think there's also a lecture from last year's summer school by Mario Mota that I think does a similar kind of like lecture on quantum simulation. I believe he talks more about how quantum dynamics gets used, I think.
Yeah. That's another good one. Let me go to the next one. In your experience, which QPU-based quantum simulation method, Trotter approximation, phase estimation, VQE or SQD, is the most effective to introduce in an educational context, and why? Particularly thinking of high school or early undergraduate students beginning to explore quantum computing.
That's a good question. I would probably say, um, I think probably the Trotter approximation and phase estimation are maybe the two kind of like most approachable topics. I think VQE maybe as well. Like so long as the students have sort of a relatively like basic foundation in quantum mechanics, they should be able to understand how these things work. SQD, I think, is maybe a little more advanced, but I think could be helpful in maybe like a higher level undergraduate class or a grad class. Um, and yeah, and then high school I think is tricky too because you also have to. I think maybe for high school, the Trotter approximation or phase estimation I think would be the two best ones because I think phase estimation really sort of demonstrates the sort of non-intuitiveness of quantum mechanics and like how interesting the field is to a large degree, at least in my opinion.
It could be a follow-up of after introducing Schrodinger equation and in general dynamical evolution of systems when
Yeah,
we're simulating them with quantum computers. But ultimately, as you said, depends a little bit on what has been also taught before, right? So it depends on a lot on that. Okay,
yeah.
so let's pick another question. Why should we use gate-based quantum computers to simulate molecules? Aren't quantum annealers more suited?
This
That's
is
an interesting one.
yeah, that's an interesting one. Um, I think the argument for using gate-based quantum computers um, feels similar to there's this kind of like differentiation in quantum simulation between digital quantum simulation and analog quantum simulation. At least that's what this question is sort of making me think of. Where in digital quantum simulation, you can truly simulate any type of system that you want. It can have whatever symmetries you desire, whatever Hamiltonian you want. It can have whatever interactions in that Hamiltonian that you want to include. And that's digital quantum simulation is what you would use gate-based quantum computers for. Analog quantum simulation is much closer to building an experimental apparatus that will behave similarly to a system that you want to simulate, but it's restricted to that particular system. So like quantum annealers would be good for like spin lattice type kinds of simulations and models, but aren't universal and may not be able to simulate something like a chemistry, like an arbitrary molecule, or maybe some kind of like particle physics simulation you wouldn't be able to do with those kinds of systems.
Absolutely. Um, we actually move now from questions related to the lecture to questions related to you and your career, which I think is something we
Mm,
wanted to cover anyhow. So I think it's a perfectly a
cool.
perfect bridge. And we got two questions. One is, how did your background or experiences outside physics influence how you approach research or teaching today?
Oh, that's such a good question. Oh my gosh. Um, yeah, so I think my experiences outside of physics, I think have especially taught me um, how to consider a sort of like a diverse set of like backgrounds and like foundational like levels of knowledge when it comes to teaching. Um, and so the what that has done for me is what that how that has influenced me in the way that I teach has been to learn how to like approach science communication by sort of describing a particular topic or concept in a few different ways that are relatively sort of parsable. Um, and that's I think like one thing that's done. I think the other things that have happened to me is the experience I've had outside of physics have also taught me about like research and like resource disparity, if that kind of makes sense. Because like in the research field, you're always like trying to find different grants. There are lots of interesting people doing really cool work that may be at institutions that may not be as well resourced or whatever like that. And I have always found myself like really not focusing on them, but like paying attention to them maybe more than others. And I think that has proven to be really helpful in finding like new and interesting ideas like in the field.
Yeah, yeah. And actually, I just want to also add a comment since this is also a little bit what I am doing in
Mm-hmm.
regarding of the education mission. I think it's really important to have people from different backgrounds. And I'm saying this as a physicist, since my background is this one, and a lot of people working in quantum computing today have this type of background. I think having different angles and different
Mm-hmm.
experiences is invaluable.
Yeah.
And since the field is moving in this direction, we should not restrict ourselves to look from a specific angle, but really to open it up as much as we can.
Yeah, 100%.
Um,
And another point that I can add to that too is like another thing that I come with that a lot of other sort of folks with a physics background don't as strongly. I think I come with like a relatively solid, or at least stronger than most of a lot of my peers I've talked to, like software engineering background, like proficiency in like how GitHub works and what continuous integration, continuous development is, like how to work with stuff like in the cloud, or like manage different sort of like software engineering kinds of resources. I think is really valuable because you can take a synthesis of like a physics background knowledge and a sort of software engineering knowledge to make really powerful tools that other people can use.
Very, very true. Absolutely. So I think I lost a little bit. There was another question related to your job. Maybe this one. What part of your job do people misunderstand the most?
Misunderstand the most. That's really interesting.
Yeah, that's
Um, hmm. I think maybe it's sort of, at least with my job, it's um, maybe the extent to which that like a lot of my job is science communication. Because like I'm mostly like I mentioned earlier, like I mostly write the software documentation for our platform. Um, and what that requires is sort of kind of like a holistic understanding of like all of the different software products that we have and like the different software packages that people can use, how they interact with each other, and uh, how to sort of like bring a user to the level of knowledge of being able to like use them across different arenas or whatever application area they would want. um, and also, when we have tools that come out like the Qiskit add-ons, like the SQD add-on, the circuit cutting add-on, things like that, um, a lot of that work is based off of research. But what we want to be able to do is to have people who aren't as familiar in the field or don't want to necessarily understand like how the underlying sort of package actually works, or at least have like a working, or at least just need a working level knowledge. A lot of what I do that is actually turns out to be a little tricky is how do you condense all of that information in a way that's parsable to someone that doesn't necessarily have the same background as someone who would just be reading the article that it's based on in the literature.
Yeah, that's definitely one of the major challenges. I fully agree. Now I think we move back to like questions related to. Oh, actually, maybe we stick still to possible careers,
Okay.
since there's a question also up there which says, "Is it difficult to get involved in quantum machine learning?" And my background is a machine learning engineer with degree in physics, with experience implementing some of the basics algorithm. So maybe somebody with a background in quantum machine learning, how do you see this type of profile for a
That's a
career in quantum
good
computing?
question. I don't know how strongly I can comment on like how difficult it is. Um, but what I can say is that with a mixture of backgrounds like you have of physics and machine learning, one of the things that the field of quantum computing I think really thrives on is having that diversity of backgrounds. So being able to find the interdisciplinary places in between your physics background and your machine learning background, I think finding those places and using that as the niche to sort of like wedge yourself into spaces that you want to be working in, I think is like a strategy that I think works really well, and that is I think rewarded in the field.
Yeah. I'm looking at the next question, which is now is back on more. So we leave the career topic at least for the moment, and we are
Yeah.
back on the simulation. So the next question is, I've heard the claim that to simulate a molecule of caffeine correctly, around 160 qubits are required. Given that statement and the fact that quantum computers available today can have that amount of qubits, is it actually feasible to simulate that molecule with a reasonable amount of noise? That's
Yeah,
a
this is a good question. And I think the qualifier here is that, sure, maybe we have enough qubits to do that, but it depends on the type of simulation that you're wanting to try to accomplish using a QPU and what is the corresponding circuit depth of the simulation that you want to try to accomplish. Because if your depth is still quite large, then you'll still run into like noise and sort of having results that are like really hard to interpret or just basically don't tell you anything. And so the trick now that we have enough qubits to do things like simulate caffeine is to figure out what is the most efficient approach to use a QPU to simulate that molecule, and what error mitigation techniques or what combination of error mitigation techniques and what different kind of like tricks related to that to suppress and mitigate errors will allow us to execute circuits that are that large without with a reasonable amount of noise.
Yeah. Yeah, exactly. And also, I think there is a bit of a misconception between physical and logical qubit. And
Yes,
I think in this case, the 160 qubits required are supposed to be on a fault tolerant quantum computers and not the physical qubit we have nowadays. So for doing that type of simulation, we can approximate with error mitigation, other type of simulation approaches that Kaelyn has mentioned in the lecture. But I think for nowadays, we can still simulate a caffeine molecule precisely, and we need to wait most likely 2029 for fault tolerant quantum computers, right?
that's the plan at least. Yeah.
That's the plan. um, then we move on to the next question. I'm scrolling down. Oh, that's an interesting one. How long do you think it will take for quantum computers to become mainstream?
Ooh, oh, that's an interesting question. To become mainstream, I think that's I think am of the opinion that quantum computing, because of how niche the applications are, I think it's going to be really hard to kind of like break out into the mainstream, so to speak. Um, like I guess like the kind of recent analog that you could look to was sort of like the whole like AI boom, because like the thing that those models do is something that's like very obvious to see and very obvious for like just like a regular person to use. But with QPUs, it's much harder to really understand like what are the useful application areas that I can do, how do I use them, and like how does it affect me, because a lot of people are very much are less interested in understanding how quantum computers work and more interested in how are they useful to me. And I think if we can figure out that branding, or that way to sort of like communicate that message, I think that's really where like quantum computing will kind of, and like I think probably sometime after we get to advantage and fault tolerance, I think that combination of things I think will help it kind of like push out into the mainstream, at least like to some degree.
Yeah, yeah, I fully agree. Uh, Although I think one could also say, perhaps on one end, I fully agree. I mean, if you're talking about scientifically,
Yeah,
of quantum computing, I'm on the same page. But perhaps mainstream is a very, let's say, generic term that I guess could be seen in different
it's
ways. And
true.
if you think about it, quantum has already appeared in mainstream Hollywood blockbuster. I think
Exactly.
on the other hand, I think
Right.
quantum is already mainstream in a certain way.
Yeah,
Not the most
exactly.
accurate, but
Right. No, that is true, because like our modern world is built almost entirely on quantum mechanics. And like it's just one of those things that like we spent a long time figuring out through the 20th century, over the last 100 years now, because it's the year of quantum, and using those to build the current modern technologies that we do are all most if not all like quantum based.
so let's now move on to the next question. This was a very interesting question. I really liked it. Um, so it appears that you are performing your simulation using time-independent Hamiltonians. How do you model time-dependent Hamiltonians?
That's a good question. Um, I think the way that you would do that is, I could be wrong on this, but I believe how you would do that is you would model in sort of like adiabatic time evolution, where you would do a similar thing where you have a time evolution operator that you have to traurize in some way, but the operator itself changes with time, and changes from essentially like one Hamiltonian sort of smoothly to the other. I think is sort of like the very quick, simple answer of how that works.
Um, next question then would be I don't know if you're an expert on that, but maybe interesting. Does quantum computing have future applications to computational fluid dynamics?
Oh, that's interesting. I don't know for sure what the application areas would be, but I have seen work come out in the field related to fluid dynamics. Actually, for example, one of the new Qiskit functions that we came out with, I think it's Quick PDE or something along those lines, has a fluid simulation as its example of, of how to use it. So there is an application area, or at the very least, it's being explored, and we're trying to see what can quantum computers provide in terms of efficiencies in trying to enter that field.
Now we have a question related actually of applications or different applications of quantum computing beyond quantum simulations. And the question is, in the lecture you talked about simulating physical systems. Will this method be used for simulating other NP-hard systems like financial systems, for example?
So this is
General
actually
applications of quantum computing.
right. Yeah. So this is an interesting question, and I think you kind of like the asterisk kind of touched on one of the things about finding application areas of quantum computing, because I think using these principles of simulating quantum systems, things like QAOA and VQE and SQD and things like that, are all based on taking advantage of physical laws and Hamiltonians and simulating them in some way. So the trick, I think, with trying to understand or characterize other NP hard problems like financial systems, for example, is thinking about, okay, how do I take this problem and represent it in terms of some kind of toy physical system that I can then model or simulate using a quantum computer? I think that kind of bridge is where the bulk of the activity in the field kind of really sits. And is where things like the max cut problem, for example, is based on. Like you map the max cut problem to a quantum simulation problem, and you find, I believe it's the ground state of the sort of toy Hamiltonian that you come up with based on the graph that you want to find the max cut of.
If we're talking about Qiskit patterns, that would be the first step, right? The
Yeah,
mapping part.
exactly.
I think we're almost at the top of the hour, the time. So I guess
Yes.
I'll ask a last question. I don't know if we will be kicked out automatically, so I'm not sure. So in this case, I first want to thank you, Kaelyn, for this great lecture and for the Q&A. And now I will follow up with the next question, unless we are
Great.
kicked out.
Cool. Great.
Right. So let me see, because now the order changed. Is there a real world example where Grover's algorithm has been applied to improve search? I don't know if you know that.
That's a good question. I don't know if I know any off the top of my head. The way I've seen Grover's algorithm and Shor's algorithm and those others, I think until we really get to fault tolerance, is going to be like one of those sort of like educational algorithms. And the thing that's tricky with Grover's algorithm is that the demonstration of it is really simple and cool to look at, because it says like, oh, okay, I have like a certain item in a list of things that is the correct one, and I'm trying to arrive at it. And it's a really great demonstration of how quantum computing works. The tricky part is, again, with this whole thing of like trying to solve like other NP kind of hard problems, is how do you map a type of problem that you want to like some kind of search problem that you have, how do you map that to a Grover's algorithm? I think it's the really like tricky part, that like people are sort of working on and trying to figure out.
Yes. And then now we maybe that's also a very interesting question for many, since we have students of different age. A high school student who's really interested in quantum computing. What practical projects, research do you recommend I do?
Oh, that's such a good question. I think in terms of practical projects, I would first look at some of the exercises or examples that are in our learning materials. and try to be able to like do those yourself. Like either write them out on your own sort of like GitHub profile, or sort of like sit down and kind of like work through the math and really kind of like build and like demonstrate to yourself that you have that intuition. And I think from there you can kind of expand out and think about, oh, what are the kinds of projects that I could like work on? Like what are maybe like if I want to try to do some kind of like software thing. Um, I think the important part is being able to kind of understand like the pen and paper kind of like theory of it and how to use it, and then translate that into maybe some kind of software project if that's what your background is.
Now we go to the other side of the spectrum in terms of education. So we have a PhD related question.
Okay.
Does quantum simulation require a PhD to pursue as a career, where it may be molecular optimization or QML? Would it be enough to just have a master with hands-on experience?
Mm, this is a good question. And it's always one of those career questions that are sort of like tricky to answer and just like with just like a single question. I think the answer is it probably depends. I think if your goal is to be doing research, to be leading research, you want to, have like a group, maybe work at a lab or, some other like large institution as like a postdoc researcher and like be part of like collaborations and things like that and sort of like actively like be doing that, then I would say probably a PhD is maybe the right approach. But if your interest is more in I know that I want to, maybe you know that you want to land in industry, for example, or that you don't mind doing like a mixture of other things, like maybe like more of like a software engineering kind of work, um, and or like your goal is that you don't necessarily want to be like a leader in a particular field, you just want to participate in research, then I think a master's is also a good approach with some experience within industry somewhere.
I would also say, and actually, this was a question. Clearly, it's very interesting for many, maybe approaching
Mm.
this decision, because also some people have asked this question yesterday to Olivia, and
Mm,
I
mhm.
would also agree with you both gave a similar answer in the end. The short answer is it depends, right? It depends on what
Yeah,
type of career and specialization or role you want to get into. So it's not a requirement, but could be a plus, I would say, depending on the role.
yeah, yeah.
And I just got the
Mhm.
communication that actually, if I don't wrap up, or if we don't wrap up, we will not be kicked out. So
Okay,
since we are
great.
already 4 minutes over time, at least according to my watch, I guess it's time to close this session.
I think so. Yeah.
Again, thanks a lot, Kaelyn, for your first for your lecture and now for the Q&A, and thanks a lot for everybody to join this session and asking so many questions. Sorry if we didn't have the time to answer all the questions. I see there are so many actually
There's so
still,
many.
but I
Yeah.
guess I guess there is also Discord server with many channels also for that reason.
Mhm.
And I guess we'll see you later for John Pressfield lecture on quantum
Great.
simulation. So see you later.
Excellent. Thanks, Fabio. Thanks, everyone.